Section 15.5, now we're doing triple integrals in rectangular coordinates. So you should be able to, by the end, set up and evaluate integrals, triple integrals in R3. Let's start off with just some preliminary comments here, which is, as before, we can have a formal definition, excuse me, in terms of Riemann sums, but we won't really go into the formal definition in this class. The other thing that is worth me saying up front is that we still have Fubini's theorem applying. So if you have a triple integral over, say, a rectangular, or I shouldn't say rectangular region now, because now a rectangular box here. This example, evaluate the integral over b of x over y plus z squared dv. So note here, I guess it's worth me pointing out that this is now the little thing that we tack on at the end of our integrals. Now it's a little chunk of volume instead of dA, a little chunk of area, dv, a little chunk of volume here. How do we evaluate such an integral? B is x's runs from 0 to 2, y runs from 2 to 4, z runs from -1 to 1. So this is equal to integral x runs from 0 to 2, y runs from 2 to 4, z runs from -1 to 1. You can integrate this in any order here. I'm going to go in this x, y, z. Well, actually, it'll be z, y, x going in reverse order. dz, dy, dx. So first we integrate this with respect to z. Antiderivative of this with respect to z, and again, we're going to be thinking of x and y as constants. This part of the process is a very straightforward generalization of the double integrals that we did before. If you can evaluate double integrals from before, you can certainly evaluate this kind of triple integral. Plugging in z is -1 and gives us -x over, z is 1, -x over y plus 1. And then plugging in z is -1 plus x over y minus 1 dy dx. Okay, now we integrate with respect to y, treating x as a constant. So antiderivative of -x over y plus 1 with respect to y will be -x times the natural logarithm of y plus 1. And then antiderivative of this with respect to x will be x times the natural logarithm of y minus 1. Plug in y from 2 to 4. By the way, I just put parentheses here, not absolute value bars, around the logarithm argument here, because everything in sight is going to be positive, so we don't have to worry about that. Okay, so plugging in y is 4, gives us -x times natural log of 4 plus 1 is 5. Plug in y is 4 over here, gives us positive x times natural log of 4 minus 1 is 3. Okay, so now we subtract off the y is equal to 2 terms, -x times natural log of 3 plus x times natural log of 2 minus 1, natural log of 1, that's 0. Okay, so one more integration to do, that becomes 2 natural log 2x natural log of 3. And so now we can just do one more integration. I'll skip the steps here. You end up with natural log of 9 over 5 times 1/2 x squared, plug in x from 0 to 2. And so that will give us 2 natural log of 9 over 5. Okay, so this is our first example of if you can do a single integral, if you can evaluate a single integral, you can evaluate a double integral, and you can evaluate a double integral, you can evaluate a triple integral. So in later videos, we'll talk about more interesting examples, like what happens when we're not integrating over rectangular blocks. We'll also talk about the physical interpretation of triple integrals.